Hey everybody, let me tell you a secret. If you see a summation that contains any kind of trigonometric function, it's gonna telescope. If you don't know what telescoping is, it's essentially writing some expression in terms of the difference of two other expressions that, as you go through the series, end up canceling with other terms in the series, and everything just nicely collapses. And so what we have here is the sum, as k goes from 1 to n, of the inverse cotangent of 2k squared. And we want to prove that the sum of all of this, and by the way, these are in radians, that is very important to note, and we're trying to prove that this is equal to just the cotangent inverse of 1 plus 1 over n. And yeah, I first looked at this problem and my brain processed right from left to right. I see the sigma. I'm like, okay, that's fine. I see the cotangent. I start getting a little worried. No one uses cotangent. And then I see the inverse and I lose it. But I look at it and I'm like, there's telescoping, right? There's gotta be telescoping. And then I remembered a problem that another math YouTuber had uploaded, and it was very similar in spirit, and I think it may have been inspired by this problem, because this problem was not, if you've seen I Let's Solve Math Problems video, a Triggy series, he does a similar series to this, and I did not come up with this problem. I found it in a practice set for Olympiad trigonometry. So I don't know if his problem was inspired by this or what, but these are, so I remembered that problem and I was like, well, it probably going to telescope similarly, but I didn't know an addition formula. He uses sort of the addition formula for tangent and goes on to explain like all the telescoping and stuff, but I was like, well, I don't know any formulas for cotangent, but I'm like, well, no one does. It's not on anybody's formula sheets. So it's probably easy to get to. Now, let's look at, so if we want something to telescope, right, we basically want A to equal B minus C. So we want a formula that lets us take some inverse cotangent and express it as the difference of two other inverse cotangents. So let's look at tangent of A minus B. This is equal to tangent of A minus tangent of B divided by 1 plus tangent A times tangent B. And cotangent and tangent are reciprocals, so I thought, well, why not just take the reciprocal of both sides? And so you get the following formula. Cotangent of A minus B is equal to 1 plus tan A tan B over tan A minus tan B. But everything's still in terms of tangents. However, it's pretty easy to notice that we can divide both the numerator and the denominator by tangent A times tangent B, and everything will turn into cotangents. Exactly, it will turn into 1 plus cotangent A cotangent B divided by cotangent B minus cotangent A. Right, well now, suppose we replace A and B as inverse cotangents, then, so basically we're saying that A is equal to cotangent inverse x, and b is inverse cotangent y, then we get the equation, this equation, and we see that we almost have gotten, or on the right hand side, there's no cotangents or cotangent inverses. But remember that we're looking at this trig sum, and we're dealing with inverse cotangents, so it's pretty easy to just take the inverse cotangent of both sides, and we get the addition formula that we wanted. Specifically, we want x and y such that 1 plus xy divided by 1 minus x is equal to 2k squared. Well, we can sort of just guess and check, which is what I did. And first of all, we sort of have this plus 1 and a square, and so I'm thinking, okay, maybe, we get a difference of squares, and, difference of squares usually have some nice cancellations when you subtract them, and so then, like, when you multiply them, you get the minus 1, and then you're just left with whatever's on top divided by the nice cancellation on the bottom. In summary, I'm just trying to give sort of intuition for what is essentially guess and check. But if we choose y to be 2k plus 1 and x to be 2k minus 1, we notice that 2k plus 1 minus 2k minus 1 is equal to 2. And if we multiply these two together, we get 4k squared minus 1, because we get 2k quantity squared minus 1, and then that with the plus 1 just makes 4k squared. 4k squared over 2 is indeed 2k squared. So we have that cotangent inverse of 2k squared is equal to the difference of these two inverse cotangents. And so basically we slap a sigma on both sides of this equation, and we notice that 2k minus 1 and 2k plus 1, when you increment k, the next term, the positive term, will be 2k plus 1. That will cancel with the negative term previously, and then we get a 2k plus 3. And so on and so forth. So we're left with this initial one, which corresponds to k equals 1. So 2k, or 2 minus 1, is just the cotangent inverse of 1. Then, everything will have canceled except for the last negative term when k is equal to n, and we get the cotangent inverse of 2n plus 1. So now, this has all telescoped, as we would say, to the cotangent inverse of 1 minus the cotangent inverse of 2n plus 1. And we can just apply this formula for subtracting inverse cotangents in reverse. And we get that this is equal to the inverse cotangent, and we get xy is 2n plus 1. Plus 1, we get 2n plus 2. And then y minus x is 2n plus 1 minus 1. And so that just comes out to be 2n. And then we see that if we were to divide out this fraction, we do indeed get our desired result, because 2n over 2n is 1, and 2 over 2 over n is 1 over n. So we do get that this sum, after some manipulation and quote cleverness, we get the telescoping sum we desire, and we get our result. So again, like I said in the intro, trig sums always telescope. Thank you for watching, and I'll see you in my next videos. Thank you.